In section 1.3, we're looking at acceleration. Acceleration is a vector quantity. It's also described as a rate of change, specifically how quickly an object's velocity changes over time, or the rate of change of velocity. Since it's a vector, the symbol for acceleration is a lowercase a with an arrowhead on top, indicating that it is a vector. The unit of measurement is the meter per second squared. And the equation for acceleration is delta v over delta t. The Greek letter delta in mathematics means change in. So this equation can be expanded to the change in velocity, which is v2 minus v1, over the elapsed time, t2 minus t1. We're going to begin by taking a look at a new type of graph, and this is called a velocity time graph. A graph describing the motion of an object with velocity on the vertical axis and time on the horizontal axis. Here's an example. This is a graph that looks at the velocity versus time for a skateboard rolling down a ramp. As you notice, there's a linear relationship. And if you were to describe the motion of this object by looking at the y-axis and what is happening to each of the points over time, you can say that the object's velocity is increasing regularly over equal intervals of time. And it appears as if the object's velocity is increasing over time. What mathematicians like to do when they see a graph of a straight line is to find the slope of the line. So we're going to find the slope of this graph, and we'll use 2 points. One at t1 equals 0 and t2 equals 10. We're going to have to take a look at the velocity at t1 and the velocity at t2. Slope is equal to rise over run. In this case, the rise is the y-axis, which is v2 minus v1. And the run is the x-axis, t2 minus t1. We can sub in the values from above. v2 is 30 meters per second south. Be sure to include units in direction. And v1 is 0. Divided by t2, 10 seconds, minus 0. If we simplify this, we are left with 30 meters per second south divided by 10 seconds. So the slope is equal to 3 meters per second squared south. This is the acceleration of the skateboard. So let's remember this. Whenever you have a velocity time graph, the slope of a velocity time graph gives the average acceleration of the object. There's another piece of information you can collect from a velocity time graph. This is the area under a velocity time graph. The area under a velocity time graph is important because it can give you the displacement of an object during an interval of time. So let's take a look at this slightly more complex velocity time graph. Here we see that the motion of the object has an increasing velocity from 0 to 5 seconds. And then the velocity remains constant at 10 meters per second south for the remaining 5 seconds. What we want to do is determine the displacement of the velocity time graph by finding the area under the curve from 0 to 10 seconds. So what we're going to do is find the area of the shapes represented underneath the graph. And I'm going to break it up into simpler, more identifiable shapes. For example, during the first 5 intervals, the graph forms a triangle. And we'll call this area A. If we determine the area of triangle A, we will know how far the object has traveled during the first 5 seconds. Similarly, we'll find the area under the second segment, which forms a regular shape, a rectangle. If we find the area of this rectangle, we will determine how far the object has traveled for the final 5 seconds. So let's do this. So the displacement under the curve for segment A will equal the area of segment A. And area A would be the area of a triangle, base times height divided by 2. The base of this triangle would represent this right here, 0 to 5 seconds. This is known as the elapsed time. And the height of the triangle would represent this right here. And this would be the velocity from the triangle. So if we sub these values in, we end up with 5 seconds times 10.0 meters per second south divided by 2. Simplify this in your calculator, and you are left with 25 meters south. We'll do the same for area B. Area B is a rectangle. And the formula for the area of a rectangle is base times height. So let's take a look at these values. The base would be the elapsed time from 5 to 10 seconds. And during that time, an additional 5 seconds passes. The height can be measured off the graph, and this would be 10 meters per second south. So let's plug these values in. 5 seconds for the base, and 10.0 meters per second south for the height. Simplify this into your calculator, and you are left with 2 significant digits, 5.0 times 10 to the power of 1 meters south. In order to find the total displacement that the object has traveled for the entire trip from 0 to 10 seconds, we would have to add up these values. So 25 meters south plus 50 meters south, written in scientific notation as 5.0 times 10 to the power of 1 meters south, is 75 meters south. And that is the total distance traveled by the object for the entire trip, 0 to 10 seconds. Let's continue on to problem solving using our equation for acceleration. Sample problem number 2. A bullet is found lodged deeply in a brick wall. As part of the investigation, a forensic scientist is experimenting with a rifle that was found nearby. She needs to determine the acceleration that a bullet from the rifle can achieve as a first step in linking the rifle to the bullet. During a test firing, she finds that the rifle bullet accelerates from rest to 120 meters per second east in 1.3 times 10 to the power of negative 2 seconds as it travels down the rifle's barrel. What is the bullet's average acceleration? Let's start by identifying what's given in the question. We are given this value here, 120 meters per second east, and this value here, 1.3 times 10 to the power of negative 2 seconds. So writing down what's given, this bullet reaches a velocity of 120 meters per second east in an elapsed time of 1.3 times 10 to the power of negative 2 seconds. And our job is to find the acceleration of this bullet. We're going to use this equation here. Acceleration is equal to v2 minus v1 over delta t. Only problem is, this question doesn't give us explicitly the value for v1, and the value for v2. But if you notice, there's a piece of information that's implied, and that information is right here. It tells us that the object starts from rest. Whenever this is the case, we know that the initial velocity of the object is 0. So that means that 120 meters per second east was the final velocity. It's important to distinguish between v1 and v2 in order to solve this question. In addition, if you don't pick up that from rest means v1 equals 0, then you will not be able to solve this question. This is a trick that physicists put in their problems all the time. So if you've seen it once, you will see it every time. So let's substitute these values. v2 is 120 meters per second east, v1 is 0, and the elapsed time is 1.3 times 10 to the power of negative 2 seconds. Simplify this with your calculator, and you will be left with 9.2 times 10 to the power of 3 meters per second squared east. Notice this is a large value for the acceleration, and that makes sense. Bullets accelerate over a very small distance to a very high speed. That means that their velocity is changing by a very large amount in a very small amount of time, resulting in a big acceleration. Let's try sample problem number 3. When a hockey player hits a hockey puck with his stick, the velocity of the puck changes from 8 meters per second north to 10 meters per second south over a time interval of 0.050 seconds. What is the acceleration of the puck? Let's write down what's given. We are given the initial velocity of the puck, 8 meters per second north, and the final velocity of the puck, 10.0 meters per second south, and the elapsed time is 0.050 seconds. We need to find the acceleration. The equation is delta v over delta t, which again is v2 minus v1 over delta t. And we'll sub in our values. Make sure you put them in the correct order. So we have 10.0 meters per second south minus 8.0. Make sure you put in your direction. Minus 8.0 meters per second north. Divided by 0.050 seconds. Before you proceed to punch this into your calculator, you have to pay attention to the direction. In fact, anytime you are using vectors, you have to ask yourself 2 questions. Number 1, are they in the same direction? If the answer is yes, you can proceed algebraically. If the answer is no, then you have to make sure that you report them both to the same direction. You can do this by changing the sign of one of the values. So let's keep everything south. we end up with 10 meters per second south. Change the sign, plus the direction to south of the second one, plus 8.0 meters per second south, divided by 0.050 seconds. Notice that this drastically changes the value that you would get. So it ends up being 10 meters per second plus 8 meters per second. If you punch this into your calculator, you will get two significant digits, 3.6 times 10 to the power of 2 meters per second squared south. This example in particular highlights the importance of paying attention to the direction and making sure that when using algebra to answer these questions, that all quantities are listed in the same direction. Sample problem number 4. A racehorse takes 2.70 seconds to accelerate from a trot to a gallop. If the horse's initial velocity is 3.61 meters per second west, and it experiences an acceleration of 2.77 meters per second squared west, what is the racehorse's velocity when it gallops? So we are given an initial velocity of 3.61 meters per second west, an elapsed time of 2.70 seconds, an acceleration of 2.77 meters per second squared west, and we want to know what v2 is. In fact, this is a very common question in physics. Determine the final velocity of an object after a certain set of conditions. So our equation for acceleration is equal to v2 minus v1 over delta t. And we want to solve for v2. So what we have to do is get rid of this delta t first. So we're going to cross multiply so that we have acceleration times delta t equals v2 minus v1. Our next step is to bring this negative v1 over the equal sign. When we do, its sign will change. So this becomes a delta t plus v1 equals v2. In fact, this is a very common equation. We use it all the time in physics, and we normally write it like this. We rearrange the variables so that it reads v2 equals v1 plus a delta t. Now we can sub and solve. v1 is 3.61 meters per second west plus 2.77 meters per second squared west times 2.70 seconds. Let me make some room. Ask yourself if all of the directions are collinear and if they're all expressed in the same direction. For this question, the answer is yes. If we simplify this in our calculator, we will end up with the three significant digits, 11.1 meters per second west. Please try the practice problems and view the solutions online if you need any help.